So each node with the packet sends waits for an interval of time inversely proportional to the priority of the highest priority of the message. So priority ಜಾಸ್ತಿ ಇದ್ರೆ it will be sent very soon. If it is priority lesser, it will be waiting for a longer duration. After waiting, it sends a signal that is again same as CSS message. It is waiting for channel to be free. If channel is busy, yes, you have to presume that somebody with a higher priority is transmitting. That is virtual time protocol. The priority based token ring protocol, it's again, as we have stated, operates in two modes. One is a reservation mode and free mode. So the reservation and free mode, and it has two fields. One is a mode bit, another which indicates whether that frame is circulating in terms of reservation mode or free mode, and the priority of the message it is carrying. So payload, it is some payload or some bits with respect to particular node or message it is uh, carrying. What is the priority of that is recorded over there. So while it is circulating, so what happens is, if somebody has a message higher than this priority, he records the priority over here, and this in turn has to reach the other end. So whoever has initiated a transmission will receive this particular packet after rotation. So it's a token ring protocol. So after this packet or frame, after passing through the ring, has to reach the initiator finally. Whenever he receives it, he checks the priority number. So if at all he sees a higher number, so now nanak anta hakide, somebody has put a 5, and we assume that higher the number, higher the priority with respect to that aspect. If we go ahead with respect to that, then he sees that yes, now there is some other person who is having a higher priority than me. The node priority comes out with respect to whatever the messages it is holding. So you are having messages which are having high priority, then node priority is going to rise. If the messages the node wants to transmit are having a lesser priority, then automatically the priority of that node goes low. That's with respect to the whenever we are speaking about priority. So priority is with respect to messages you are transmitting. It is not about who are you and what are we speaking about. So once that is done, it is records it. So somebody is more important than me. Once I see to it, then I will set or change the mode bit from reservation mode to the free mode. So in the free mode, again, you just remember it is in a token ring, and it has to reach the person or reach the particular node which has set that particular priority. So whenever it sees that somebody has set 5 and that person notes it, now it is in a free mode, so he immediately occupies that. So he will make it reservation mode again. So mode bit is changed, and he has his own payload. So he puts it the payload, and it goes for transmission. It goes across the circulation as such. So IEEE 802.1 supports assigning priorities to the messages. So priority is stored in reservation field. So messages are split into frames, so that goes for every frame or packet can be. Yes, anybody wants to say something? Yes. Okay. As token circulates, reservation field is checked by each node. A node having a higher priority message records its priority in header. So it manipulates that. It fills the priority of the message it wants to transmit, or its priority or node's priority, into that particular message. The sender node checks the reservation status of the token when the token returns. So if it is the same as that particular nodes, and he has still some packets or frames to be sent, he continues. Otherwise, if it is higher, then it sets that particular token as free. After one complete circulation, the higher priority node that made the reservation captures the token and starts transmitting. So it has to reach the higher priority node, or whoever has manipulated that priority bit with his priority. So he gets a chance to change the token from free mode to occupied mode or reservation mode. So then afterwards, he starts supporting his payload onto the packet or carrier, that whatever the token that is being transmitted. So some important observations and theorems that are derived from pertinent to IEEE 802.5 protocol is: the minimum time required to complete transmission of a frame is maximum of f comma theta. So where f is a frame size, so including that mode bit, parity bit, the priority bit, and payload. So whenever I'm in a transmission, I cannot be stopped intermediately. I have to complete my transmission, or I should accomplish my transmission completely. If in that case, so I don't know what is the payload size as such. So that is frame size. All the bits are transmitted. Variaf is the frame transmission time. Theta is the propagation time. What is the propagation time? Or the propagation time in general is if I manipulate anything onto the transmitter, how much time it has to take till to reach the receiver. That's a normal definition as such. Now we are speaking with respect to token. So propagation time is the token rotation time. So by what time the token will come back to me. So that is theta time or propagation. The node does not transmit next frame until it has completed the last bit of the frame. It has received the header of the transmitted token back. So either maximum of those two. So I have to wait till all my bits, whatever I wanted to transmit, or the frame or whoever is transmitting has completed, or they have completed, or I initiated certain transmission. After that, the token has returned back to me. So whichever is maximum among these two will be taken. Okay, minimum time required to complete transmission of frame is max of f comma theta. So anything about that. A higher priority packet might undergo inversion for at most immediately if it missed out some aspects. It is something similar to your second chapter 2f minus GCD of f comma pi. So something similar to that. If I just missed some stuff, so I have to complete the current transmission, and then token has to return back to the initiator. Then only he can set it free, and hence 2 times the max of f comma theta time units. So higher priority packet may go under inversions. Somebody is having higher priority, but the realization happened bit later. So there was some jitter kind of stuff. So with which you got a chance with respect to whatever the priority number you are having. So he feels absurd, or the inversion, priority inversion happens over there. So the reservation mode completes, the node receives the token in the free mode, and then he transmits. So one more protocol with respect to bounded access as such is window-based protocol. It is a global priority-based protocol. The timeline is divided into frames. In current transmission, the window is defined by low to high, and only the frames or packets whose priorities are between this range, low to high, they are able to transmit it. Fine. There is a possibility of more than one node transmitting at the same time frame. It will lead to collision. So whenever collision occurs, on collision, every node increments the value of low. So you have reduced your range. Low to high of the range ittu, now you have incremented low, and hence the range has been reduced. That's what is happening over that. On free frame, every node. So if you find that on that particular window that was free, now every node decrements the value of low. So you are increasing your range. So the packets with whatever the priorities they are having, they can be transmitted because something is free. Somebody can attempt to occupy the channel. That is the intention. It's something similar to binary search. That's why there was a confusion in the last class as such. So where low minus high, or the how do you search a particular element in during binary search? If you can just imagine that particular stuff. So if that was with respect to IEEE 802.5. Bounded access protocols, particularly for LANs, so local area network. The following are two popular examples. One is IEEE 802.4. Now, the token holding time is what we missed out in the previous 802.5 architecture, so the definitions as such. If somebody gets it, he holds it for until he completes all the transmissions as such. If there are many contenders, or the equal priority, or the more than one priority authorized, if we start assuming that kind of scenarios, then there is a chance that the message validity may go on varying, or the higher priority messages may not get the chance. If two are at the same level of priorities and one is not getting a chance to transmit, then what happens? So it can be used in both token ring and token bus networks. So token bus is, so basically there is a virtual ring that is formed. It's also known as a time token protocol, so that there is a bounded access. Every node is permitted to transmit only during a restricted amount of times. So there is a speculation, and as in case of previously we stated about scheduling algorithms with respect to tasks as such. So we have come to terminologies called as a synchronous foreground and background tasks. Foreground tasks are for which you have planned schedule. Background tasks are normally the tasks, aperiodic and sporadic tasks are normally called as a background tasks. So whenever you have a slack time in whatever the algorithm you are using, so then they can be accommodated over there. Similar to that, 802.4 addresses with respect to messages that are to be transmitted. So synchronous communication and asynchronous communication. So whenever you have a fixed rate of communication or CVR kind of stuff, so which normally we call it as foreground or synchronous communications. Asynchronous communications, randomly some messages are arriving at particular nodes. So they are dealt at something with respect to slack time. You have transmitted whatever you could transmit, but still the token is with you, and some messages has arrived asynchronously, and if it can be accommodated, you do it. So that is how the entire architecture of 802.4 is devised. But basically the theme is, only one person should not hold the entire channel, the master of the channel, for longer durations as such, so that you fairly distribute the channel utilization, and hence accomplish the real time scenario. So task deadline missing or messages are missing, there they are still relevant. So they're relevant with respect to their timings that are being guaranteed. So how do you make that happen is target token rotation time. So as in 8.5 as well, so there is a token now. Expected time between two consecutive visits of token to a node is called as a TTRT. So theta, whatever you taken previously, is your TTRT of target token rotation time. So this is an important design parameter. So whenever a network vendor gives you a network, so that he says that initially he defines TTRT. So because payload and other issues are not there, but just I will send something. So after this time, my token comes back to the initiator as such. So real-time messages are assumed to be periodic, and hence we state something like a CBR, constant bit rate traffic, or the traffic is more predictable and hence called as a synchronous message or synchronous traffic. While non-real-time messages are called asynchronous, and they are occasionally taken up or randomly taken up if there is a slack time, or within allotted time, you can time, then you can carry out the asynchronous message as compared to scheduling of tasks, aperiodic and sporadic tasks. Each node is allocated a portion of synchronous bandwidth. So every node is allocated synchronous bandwidth. How much bandwidth will have that computations? So synchronous bandwidth is allocated so that it can accomplish its transmissions or communication. When a node receives the token, it transmits the real-time messages. After completing transmission of synchronous traffic, the node can transmit asynchronous messages. More bandwidth allocated, so you have the token holding time. There is some prediction or boundedness that is incorporated in 802.4. So TTRT, target token rotation times. Token rotation time is theta. So the theta is propagation time. Token comes back to me with respect to initial vendor agreements. Andre yaro somebody has set a network, and this is a token rotation time that is he is giving to me. So target token rotation times with respect to different nodes and their holding times, HI, comes out to be in picture. So that's where TTRT has some additional terminology. What is meant by holding time and other things will come in later part as such. Bandwidth of node. So asynchronous overrun is you are transmitting in the slack time of the time left out after transmitting the regular traffic or synchronous traffic. You transmit the any random message or sporadic asynchronous message that have arrived into your stack node as such. Worst case time between two successive visits of a token is again 2 TTRT. You will receive back your token after two times or 2 TTRT. So it has once it has missed out some one rotation and the next rotation rounded up. So for a node using a synchronous mode, time between consecutive token arrivals time is limited by TTRT. So within TTRT or between next time, synchronous mode ಅಂದ್ರೆ ಇಷ್ಟರಲ್ಲಿ ಬರಬೇಕು ಅಂತ TTRT target token rotation time. Fine. This is how the ring architecture of 802.4 should be visualized or looks like. Assume that node Ni has a message with the shortest deadline. So it has to reach within delta time. TTRT should be set to a value lower than delta by 2 because 2 times. So once you may have just missed out and the second time it has reached you, then you are allowed to transmit. Okay, with that aspects, minimum delta by 2. If the deadline of a task or the message validity is delta, so you should TTRT should be target token rotation time should be less than delta by 2. That's a design parameter you are deciding with respect to the deadlines of the messages as such. If TTRT is greater than delta by 2, so then you may not be able to occupy or reserve the token, and yes, you miss the deadline, and that may happen. ಅದಕ್ಕಿಂತ ಮುಂಚೆ ಹೋದರೆ ಸೊ ಬಿಫೋರ್ somebody occupies or there are more collisions that might be happening. So TTRT minus data. So then for what duration you are occupying, so what is the channel bandwidth allocated for you, what is the duration for which you are allocated for ith node, how much is the bandwidth allocated is TTRT minus RT. So this is the communication bandwidth for certain duration. How much in comparison with in totality, that is seen. So we can see an example over here. So N1 needs to transmit 1 MB of data for 300 MB6. So this is the amount of data. Ti is the duration with which it has to accomplish that particular task. So that speaks about bandwidth. 1 MB divided by 300. N2 needs to transmit 1.2 MB for 500 milliseconds, and 3 needs to transmit 2 MB of data for every 200 milliseconds. So minimum timing for the deadline is 200. So select a suitable TTRT ignoring propagation time. So theta is not given or not taken as such. TTRT minus theta 0 togondre TTRT 200 divided by 2, that comes out to be 100 milliseconds. Now you compute the bandwidth one because it is in terms of Mbps ಅಂತ ಹೇಳ್ತಾ ಇದ್ದಾರೆ, and hence 8 bits are to taken further. 1 into 8 divided by 300, 1.2 into 8 divided by 500. So this is the duration with which you are holding, or every node, or node 1 is holding for 21.18 seconds, and node 2 is holding for 15 point, and so on. So exercise problem, you can solve this with again substitution. I'm not much bothered about this as such. Even you can get the solution, or there is a solution manual available, you can check out. But anyway, first you try and then try to verify the things. The countdown protocol should work successfully. I don't think the statement is sufficient enough to make any true or false judgment for the matter. Anyway, he has given. We'll just try to attempt that as such. Irrespective of whether priority arbitration starts with either MSB or LSB, the message priority value, as long as agree on conventions. So if MSB, then it will be fair enough. You are making much decisions, you need not wait for all the transmissions as such. Even anyway, you have to, if I say that you have to transmit complete ID, so there was a bus condition, automatically bus will choose with respect to word and word or operation. So something is selected with respect to parameter, and hence I will not really bother about that. So then one more protocol apart from your 802.4 bit rate. So re-ether or real-time Ethernet is a protocol. Normally the Ethernet IEEE 802.3 whatever you are having. So CSMA-CD approach is followed, but how do you make it suitable for real-time traffic is what is addressed in this particular rather or re-ether. So it stands for real-time Ethernet, switches between Ethernet and a token ring protocol to provide timing guarantees to the time applications. Whenever real-time traffic comes, then you go for a token ring protocol to provide timing guarantees. So otherwise you work as a, or non-real-time traffic is normally addressed with respect to the CSMA-CD kind of stuff. The protocol switches seamlessly to either mode or for real-time messages. Again, repetition, transits back to CSMSED when all real-time sessions are terminated. So it is up to the node to decide whether to go for a CSMSED or normal Ethernet or rather. In case of real-time request, if the network is not in rather mode, a switch to rather message is broadcasted. So it is a network or it is communication across nodes whenever you are switching. So now there is a real-time traffic has to be intimated to everybody else. So that has been transmitted with respect to broadcast. All nodes that receive message switch to reader mode, also acknowledge the sender. The currently transmitting node waits for ongoing transmission to the end, then sends an acknowledgement. After receiving acknowledgement for all nodes, the initiating node creates a token and circulates. So automatically what you have done is you have communicated. From now onwards the rules of the game change, and now it's not Ethernet, it's rather, and it's token ring now. So with which we will start operating. So once everybody agrees, acknowledges the same, so then you switch to rather mode. So more than one node can initiate, so the real-time scenarios start arising. So simultaneously there can be many transmitters. An initiator A sends acknowledgement to another initiator B only if B's node is smaller than A's. So anyway, you are switching to other mode and you communicate if that whom to communicate. So you choose a certain mechanism so that communications are reduced. In case of loss of acknowledgement, the initiator times out. So initiator retries a fixed number of tries. After that, it just assumes that that particular node is dead. ಎರಡು ಮೂರು ಸಲ ಹೇಳಿ ನೋಡ್ತದೆ, then it is not switching to another mode, or you are not able to receive the acknowledgement from that particular node. Whenever you say that this is important, please listen, but it is not listening, then yes, the network decides, or that set of nodes will decide over or entering the token ring will decide that that is out of the ring as such. Rather uses a time token scheme. At any time, only one real-time request is allowed per node. So you can occupy with respect to whatever the messages you are having. You may be having multiple messages, only one real-time request. Anyway, you can have many messages, but anyway you are switching. So ether into ether madbekar one request is sufficient. Each real-time request needs to specify required transmission bandwidth based on the amount of data it needs to send. So that is what is CI by TI. We have computed how much data and within what time you have to send that. That speaks about the bandwidth. This time interval is target token rotation time. So you decide upon what is TTRT now with respect to that aspect as such. Nodes are divided into two types: real-time set RTS, non-real-time set NRTS. It is as good as synchronous and asynchronous traffic. Nodes can reserve bandwidth for each session. While circulating, the token visits each node. A node having a token transmits its RT data and passes to the next node. It is somewhere again similar to your rate note 0.4 ಆಗ್ತದೆ, but you will fix up some mean holding time ಅಂತ ಹೇಳ್ತೀವಿ, MTST ಅಂತ ಬರ್ತದೆ. ಅಲ್ಲಿ you are having some other nomenclature. Okay. Mean token holding time. So after completing transmission, if there is no more reservations, a last node in RTS passes the token to the NRTS. So now you can switch to the non-real-time traffic as such, or CSMSED kind of stuff. Let MTSTI be the mean token holding time for node Ni, and the token is then tagged with the time to deadline. So within which you have to accomplish a communication, which is given by time to deadline, or TTRT minus mean time, that mean token holding time. So what is the significance of time to deadline parameter? When a node belongs to NRTS gets the token. So NRTS is non-real-time traffic. It determines whether there is a sufficient time to send a data without affecting the real-time traffic at other nodes. If yes, send it. Otherwise, decrease the time to deadline accordingly. It then passes the token to the next node in NRTS. If there is no time left to send NRTS data, it informs last node in RTS that it should be the first node to get the token during the next round. So that some kind of reservation is being made so that it gets that token. because it is having a higher priority message task only for the so message. The first note in the RTS, every new real-time request goes through admission control procedure. It is performed locally at each node. TB NRT be the bandwidth reserved for NRT set. MTST new be the bandwidth reserved for the new node for RTS, whatever is the new node traffic. Then real-time request is admitted only if so ಇದ್ದಿತ್ತು so whatever the current node evaluation mean time of holding time of current node whatever you are under transmission for saw entries, so then TBNRT so bandwidth requirement should be less than the total um, TTRT token rotation time TTRT. So this is how the switched real-time network looks. So some kind of a tree structure is shown over there. Modern Ethernet networks do not use coaxial cables, so you use that Ethernet cables as such. Instead, they are composed of switches. Switches are an improvement over the hubs because hubs were more often only the repeaters. Now the splitting and bandwidth management can be made with respect to the switches. Switching row advantage and so we can have that bandwidth management. So in a star topology means, but as per this, it looked like a trees topology as such. Star means one center and remaining, or most oftenly a hub to different nodes in because that is called as a star topology. In star, there is a dedicated cable in each direction that are therefore collision cannot occur on any cable. However, switches do not guarantee which packet will be sent first. So they are more about the bandwidth management or the splitting of the stuff. Employ a switch with bandwidth reservation capabilities. So that's why we are assessing them with respect to the bandwidth managing capabilities as such. Okay, then performance comparison based on network utilization. Next class, thoda. Okay, I think we'll deal with this stuff. I'm just going with respect to lectures, number of lectures. So again, another 100 or more. So I will take in this in next class. Any other doubts? Please ask, or else we'll leave the class. Yes.